So today in science, we're going to see briefly about population dynamics. So what is a population? So a population is a group of individuals that interact one with the other. So, and this interaction is tightly related to geography. So if they are um, near, they are going to interact more. If they are far, they're going to interact less. If their food is on mountains and there are more of those individuals in the mountains, there is going to be more interaction and so on and so forth. Other thing that is very important is density. Density is how many individuals there are per uh, per area. So it increases with births and immigration when um, individuals from other places join uh, this population, and decreases by death or emigration when individuals leave to other populations. Also dispersion, if they are all crammed together or if they are spaced from one another. Other thing that affects the population dynamics uh, is the population growth. So, for example, fecundity. For example, the mosquitoes, they only live for like 2 weeks, but they can have 2,000 offsprings, while the rhino lives 50 years and at most he can have 5 offsprings. So this is also a, and all of these they help in the population dynamics. And we have also the limiting factors. Food, for example, uh, you have to compete to get the food, so it's a limiting factor. Temperature. Uh, in 2011, there was a mosquito outbreak, and what happened? They began to reproduce so much because there were some constraints, or shall I say limiting factors, that were not limiting anymore. The food supply was the same, uh, and also the mates, they continue to be the same. But what changed was temperature, because on that summer was particularly hot, so that helped. And also it rained, so there were stagnant ponds of water, so they had space to nurse their offsprings, so that helped the the mosquito outbreak, because there were so many infected mosquitoes. So the food would be a invertebrate, because females, they suck the blood out of the vertebrates. Temperature, they need to be hot so that they can reproduce. The mates, they already had, and they needed space. So an important thing is carrying capacity. So it's the maximum number of individuals in a population. For example, we have 7 billion people in the world, and the carrying capacity is around 13 billion. Some say that uh, 1 trillion, but it's around 13 billion. Uh, so because there's not enough food, the temperature kind of doesn't matter, because it's getting hotter and hotter. But mates, if the the humanity reproduces, there will be enough mates. But the space is also something that, because the Earth is not growing up, so it's not expanding. So that's a limiting factor: food and space. And oh, also another thing is that the the quality versus quantity. So uh, normally the lower, no, not the lower, the smaller the smaller animals prefer quantity. So it's R, uh, the maximum that a a individual can have of offsprings, because they don't take much time to nurse them. They just make a lot, and they hope that at least one survives. For example, if there are predators, if there is not enough food, they hope that at least one survives. And the larger animals, they prefer to, not all, but they prefer to decay, which is carrying capacity. They only make one or two in their lifetime, and they take a lot of time to nurse them. For example, humans, we do that. So there aren't as much humans as there could be, but they take more time to nurse. And also our population, they grow exponentially. So let's say it's three times. So when there was two people, they growed their population three times. So now it's six. But now with six, they also grow in three times. So it's 18. And with 18, they grow up three times. So that is 30 plus uh, 24, 64, and so on, so on. So it grows exponentially. And you can know um, uh, the rate by adding the births minus the deaths over the whole number. So let's say that we have 100 mosquitoes, right? On the Dallas outbreak, 100 mosquitoes, and the births, okay, the deaths at the end of 2 weeks will be 100 deaths. Death numbers, but the births will be, let's say there are 50 females, and we are going to multiply each one by their total offsprings, which 2,000 offsprings. So it's going to be, so R is going to be 2,000 times 50, which is 100,000, but 2,000 minus 100 divided by 100. Okay, so this put a 4 here, put a 10. The 100,000 minus 100 is 9,999 divided by 100 is 999. So at the end of these 2 weeks, there will be 999. So it's a 999% more than at the beginning. So it gets really big, really soon. So yeah, so that's it. R versus K, carry capacity and maximum depth of offsprings.